Scientific notation, significant figures, accuracy and precision, dimensional analysis. In chemistry, we often have to use very large and very small numbers. The number of atoms in 12 grams of carbon is a very large number. It can be expressed as 6.022 times 10 to the 23rd. The mass of a single carbon atom in grams is a very small number. In scientific notation, it can be expressed as 1.99 times 10 to the minus 23rd power. The form of the scientific notation is always the same. There's a number n between 1 and 10 and an integer of the power of 10 that can be positive or negative. Look at the examples here. 568.762 can be written as 5.68762. What has been done is the decimal was moved 2 places to the left. For the number 0.0000772, the decimal point was moved to the right 6 places, and it becomes 7.72 times 10 to the negative 6. The rules for addition or subtraction are shown. You write each quantity with the same exponent. Combine the two numbers and the exponent remains the same. In multiplication, you multiply the numbers, but you add the exponents. In division, you divide the numbers, but you subtract the exponents. If you use your calculator correctly, this will be handled for you automatically. The rules for significant figures are shown. Any digit that is not 0 is significant. Zeros between non-zero digits are significant. Zeros to the left of the first non-zero digit are not significant. If a number is greater than 1, then all zeros to the right of the decimal point are significant. If a number is less than 1, then only zeros that are at the end and in the middle of the number are significant. The rules for addition and subtraction are as follows. The answer should have the same number of decimals as the datum with the fewest. Here we see 89.332 being added to 1.1. 1.1 has one significant figure after the decimal point, so the answer must be rounded to have one decimal place, 90.4. For subtraction, same rule. 3.70 has two significant figures after the decimal point, so the answer must be rounded to 0.79. For multiplication and division, there are different rules. The number of significant figures in the result must have the same number of significant figures as the datum with the fewest. So in this example, 4.51 times 3.666 has to be rounded to 3 significant figures, 16.5, because 4.51 only has 3 significant figures. In the division example, the same rule applies. 6.8 divided by 112.04 has to be rounded to 2 significant figures, 0.061. Exact numbers are numbers from definitions or numbers of objects that are considered to have an infinite number of significant figures. An example is that there is 100 centimeters in 1 meter. There's exactly 100. Or 12 inches exactly in 1 foot. So in the example of averaging the 3 numbers, you see that the divisor is one significant figure, 3, but the answer has the same number of significant figures as the datum. Each of the datum has 3 significant figures. Your answer has to have 3 significant figures. Accuracy is how close a measurement is to the true value. Precision is how close a set of measurements are to each other. If you look at the bullseyes, you have a good idea of how to express accuracy and precision. The first shows accuracy and preciseness. All of the target has been hit around the 100. In the second, we see that the data is precise but not accurate. That is, the data, the targets, are hitting close to one another but not near the bullseye. The last one shows not accurate and not precise. Everything seems to be scattered all over the place. Dimensional analysis is a method of solving problems. This is what we're going to be using throughout the course. To summarize it, determine which unit conversion factor is needed. Carry units through the calculation. Very important. If all units cancel except for the desired unit, then the problem was solved correctly. Given quantity times the conversion factor equals the desired quantity. We will be illustrating this in class with several examples.